Now, when it comes to reviewing situations whereby you've got a fastener that's holding components together, shear stress can have the following effect. So you can have a situation whereby the bolt or the rivet or the fastener is likely to fail if the material variance is lower to the components that is more or less clamping in place. You could have a situation whereby you're going to have longitudinal tearing, so this is where the tear outs or bearing failure comes into play. So we need to know what that area is. So that area would normally be the thickness of the plate, which is characterized by T, and the distance from the center of the fastener to the tail end of the lap of the plate, as shown in this diagram over here. So that distance is characterized by L0. So to calculate the bearing stress, this is equal to the applied shear force divided by the bearing area. Okay, so this is what the bearing area is calculated. So we look at that lap, and that lap is essentially a rectangle. So the area under shear, so that is denoted by A subscript B, that'll be equal to the product of the lap length multiplied by the thickness of the plate. So the lap length gives us an idea in terms of how long this laps need to be to ensure that the fastener does not tear into the material in the direction of the applied shear force. So this formula is very good to have. So if you have an idea in terms of what your design shear stress is, you can use this equation to work out what will be the minimum amount of lap required if you have a situation whereby you have to fasten the component to this configuration. Let's look at a situation whereby you have a lateral tear. So we looked at the first instance whereby we were looking at longitudinal tearing to calculate what would be the ideal measure of the lap to prevent that from happening, preventing the fastener from tearing longitudinally into the component. But let's look at a situation whereby the material variance around the fastener is minimum. So this is where we need to calculate to find out what will be the ideal cross-sectional span that the component needs to have to ensure that it can resist tearing due to the applied shear force on the component. So you have a situation whereby the material around the fastener is quite low or quite minute, then there's a good tendency of the fastener tearing through the given component. So this is where this equation comes in quite handy. So to calculate the shear stress on the plate, so that is tau P, that's equal to Ft. So Ft characterizes some form of tensile load, okay? Where that tensile load, due to the load being offset to the center of shear, okay, so that's basically the interface between the two plates, that's going to cause a shearing effect. And that is divided by AP. And AP is basically the section under tear. So this is a cross section of what we need to calculate. And that's equal to the difference between the width or the span of the component or the plate minus the diameter of the bolt or the fastener, or which would be equivalent to the bore in the plate, times the thickness of the plate, and that will give you AP. So this is basically a summary of the variables to calculate what will be the ideal material variance around the bore of the material. Now let's have a go working through a simple problem based on the concepts that we've just talked about. So for this particular event, we have a situation whereby we have a bolt that's clamping two plates together. The plates are being subjected to some form of tensile load. So the tensile load measures at 5 kilonewtons. And the offset of the axis of the load to the axis of shear creates that offset that's likely to cause shearing across the sectional area of the bolt. So our challenge here is to calculate what would be the minimum shank size of the bolt to clamp these plates together to ensure that there is an eventual failure of the bolt. So what would be the minimum size requirement? So for us to work through this problem, we're going to make some assumptions. So the first assumption we're going to make would be that the material for the bolt is probably fabricated from steel. So the yield stress of steel, we're more or less going to assume that to be around 200, or let's just use 210 MPa. All right, so 210 MPa. So to calculate the shear stress yield limit, that is approximately about 58% of the yield stress. So 58% of that would give us some idea in terms of what the ideal yield limit would be in terms of the allowable shear. So let's proceed to work along this problem together.
Now look at this problem. I'll say work along. As stated in the question, we've got two plates, so plate 1, plate 2, that's clamped together by means of this fastener, so nut and bolt. So as I've more or less inferred in our discussion, the interface between the two plates is going to create an axis of shear, or a shear plane. And this is along this plane that the bolt's going to experience the largest possible shear. Okay, so let's call that PR in there. So in the question, we're given some information that the tensile load, so the tensile force pulling the plate, so let's call that FT. We're just going to create some form of shear that's equal to shear force acted along the shear plane. So we call that the R, okay? So that measure of force will be the same as the tensile load pulling the plate. So that's been given, so VR is equal to 5 kilonewtons, which is the same as 5,000 newtons. But we need to know some information about the material for the bolt and nut. So what we're going to do is we're going to assume that the safety factor, or the factor of safety, we'll be talking about the factor of safety following our discussion related to shear stress. So that should be around the corner very soon. We're going to assume that the safety factor, the factor of safety, sorry, we're going to know that as S such as F, that is at 1, meaning that the design shear stress, design yield stress be equal to the yield stress of material. We're going to assume that the material used to fabricate the fastener is some sort of high grade steel. Right? So we're going to assume that sigma y is equal to 210 MPa, which is the same as 210 Newton per millimeter squared. These are the assumptions that we're making. So if this is the case, then the design shear stress, we're going to call that power D, will be equal to 0.58 times the yield stress of the material. This is the assumption that we're making. Okay, so in this instance, we haven't been given a safety factor, so we're going to be looking at a similar situation in determining the diameter of the bolt if given a safety factor and some other design conditions. So therefore, the design shear stress will be equal to 0.58 times 210 MPa. So bring our handy calculator and we do the next two computations. So 0.58 times 210. That gives 151.8 MPa. Moving on, we know that the yield, the design stress, so let's call that tau D, work out to be 120 MPa. To determine the diametric size needed for this particular application, we have to use shear stress formula. So shear stress equal to shear force divided by the tangential area. So we're going to use this equation. Since we're interested in the diametric span, so in terms of the bolt that we'll be given, we know that the bolt will have a circular cross section. So what we can do here is transpose this equation and make A the subject. So make it A, which is the initial area of the bolt, subject of equation 1, then area A will be equal to shear force divided by the design stress. So let's call that equation 2. The next part to do is we can either work out the area and equate the area to the area in terms of calculating the circle, or what we can do is we can substitute the area of the circle into this equation and make D the subject and work out D directly. So let's do that. So S bolt has a circular section. A is equal to the normal formula we tend to use, pi d squared over 4. Let's call that equation 3. So what we're going to do is we're going to substitute equation 3 into equation 2 and make D the subject. Okay? So, substitute equation 3 into equation 2. To multiply both sides of the equation by 4 to pi and work out the square root of both sides. So d squared will be equal to 4vr over tau d. Okay. Then we rewrite this equation. So d squared equal to 4vr over pi tau d. Okay, so we should forget the pi, because I nearly did. Okay, these things do happen, so that's part of the reason why we make it quite a double check what we write. Therefore, the required diameter d equal to square root of 4vr over pi tau d. So let's call that equation 4. So we've got some relationship to work out the required diameter of the bolt. So all that we have to do now is substitute the non-variables and work out the required diameter. So d equal to 4 times VR, so that is 5,000, Or divided by times 5 million feet. Open out the square root. So this becomes, let's bring our handy calculator. Let's work out the numerator first. This becomes 20 times 10 to the power of 3, all divided by pi times 1, 2, 1.8, 10 to the power 6. So this becomes 3, 8, 2, 6, 4, 5, 9, 8, 5, 2. That's quite a large number. What we could have just done was to just multiply by the non-digit number. Doesn't really matter. Alright, so to work out the square root, so let's work out the universal number here, times 20 times 3. And that gives us 5.2, that's 6, 8, times 10 to the power, times 10 to the power, minus 5. And that will be a meter. Okay? Units are quite important. So work out the square root. So the square root give us 7.23 times 10 to the power minus 3 meters. So multiply that by 1,000. That would give approximately 7.23. So this is the minimum bolt size required for this particular application. Now, if we're going to make this spot material bolt not come at this size, we need to look for the nearest bolt size to this value. One thing I would recommend that you don't do is to round down the number. It's better to round up the number to number 1, add a little bit of margin of safety from a design perspective, and 2, you can also look at that from a cost perspective, but again, that's something we can talk about down the line. Because it doesn't really make sense machining or fabricating a fastener to the diameter is just a waste of money. It's just best to get what's already in stock or what's already standardized. So, the best standardized bolt size to get will be 8 millimeters. Okay. If 7.5 is available, then that's fine, but I think it's best just to round up to 8 millimeters. And there we have it.
Right, now that we've worked through that problem, let's do a very quick summary to end this presentation. So as we've more or less stated previously, we're assuming that we're not factoring any safety factor, or factor of safety, if you want to call it that. So since shear stress is equal to V over A, all we have to do is transpose the equation to make the sectional area the subject of this relationship. So A is equal to the shear force V divided by tau, which characterizes the shear yield stress. So let's call it that. Thus, 5,000 divided by the yield shear stress, which is 0.5 times 210 times 10 to the power 6, and that gives us an area of 4.105 times 10 to the power minus 5 meter squared. So how do we go about calculating the diamond? Well, since the bolt is cylindrical in terms of its cross-sectional profile, then we can use the area of a circle to calculate what the diameter is going to be. So here it's up to you. If you want to use area is equal to pi r squared, you can use that. So you calculate for r, you multiply r by 2, and that will give you the minimum diameter needed for this particular application. However, as usual, I prefer using area is equal to pi over 4 times d squared. So knowing that, we make the diameter the subject of this expression. Thus, the diameter of the bolt will be approximately equal to the square root of 4 times a divided by pi. So if you substitute the known variables in this equation, and do the unit computation, we get approximately 7.23 millimeters. However, that number has been rounded up to 8 millimeters. When you're buying bolts, components as standardized parts, these don't come in sizes of 7.2, 3 and things like that. So you need to round it up to the next available size that you can get off shelf in your design application. And that slight measure of variance adds some measure of safety, some margin of safety in the applied context of the bolt in this situation. So it's always best to round up. Now, when we look at safety, factor of safety in much more context, we will delve in greater detail in terms of why this is. Okay? And there we have it. So hopefully, our discussions helped you understand the influence of shear forces and stresses when it comes to engineering materials. And as I stated, shear stresses is fundamentally what causes distortion in component. So as designers, it's very important that you do quantify and compensate for the effects of shear stresses when it comes to reviewing mechanical components in a design context. We've also had a look at different equations to enable us measure the level of stress and strain with respect to an applied shear force. We've also talked a little bit about the impact of shear failure and looked at different situations related to fasteners. And we've looked at a very simple example in terms of how we can use the concepts learned today in reviewing geometric parameters for fasteners in particular. So the next chapter will be chapter 7, where we're going to look into the concept of the safety factor or the factor of safety. Why is that significant when it comes to product design and mechanical design engineering?
Alright folks, so hopefully everything makes sense to you. So any comments that you have, can you just type it down below? And hopefully you join me in the next session. So please share and subscribe, and I'll catch you in the next section. Bye for now.